Good afternoon. On behalf of Engineers Australia, I'd like to welcome you all to our Thought Leaders series, Innovations of Forrestfield-Airport Link. My name is Amanda and I will be your host for today. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognise their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Webuild. Webuild is a major global player in the large-scale infrastructure sector and aspires to forward-looking and sustainable solutions that create growth and innovation, whilst respecting people and the natural environment under the most challenging environmental conditions. Today, we will hear from two speakers, followed by our live audience Q&A session. And I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our moderator for today, Julian Watts. Julian is a director in KPMG's Infrastructure, Assets and Places division as a leader for transport, asset management, along with serving on the KPMG Global Infratech and Information Board. Julian is passionate about giving back to the industry through roles with the Asset Management Council, the Society of Systems Engineering, the Smart Cities Council and the Australasian BIM Advisory Board. Please welcome Julian Watts.
Thank you, Amanda, and welcome again to our viewers to today's session. I'd like to welcome our two speakers for today, starting with Richard Graham. Richard graduated in civil engineering from Heriot-Watt University in Edinburgh, UK. He has over 40 years experience of working in heavy international construction, primary and hydropower, tunnelling and metro sectors. Currently, he's the project director for the Webuild NRW Joint Venture, undertaking the 2 times 8 kilometre Forrestfield-Airport Link in Perth, Australia. Immediately prior to this, he was responsible for the design and construction of the 42 kilometre long Orange Metro line in Riyadh, Saudi Arabia, the Red Line in North Doha, Qatar, and the 25 kilometre long Step Deepwater Sewer Tunnel in Abu Dhabi. Richard will be joined by Vivek Ambak. Vivek graduated in electrical engineering from the University of New South Wales and has over 10 years experience working predominantly in the transport and water sectors. His roles to date has him as the opportunity to work with both consultants and contractors on major infrastructure projects. He's currently working as the lead electrical engineer for the Webuild joint venture on the Forrestfield-Airport Link. Vivek has started his career in Sydney, where he worked with Oricon on the Novo Rail Alliance and the South West Rail Link project as a design engineer. In 2012, he moved to Perth to work with Jacobs as a design consultant on the Water Corporation and Butler Extension projects. In his current role, he's responsible for the delivery of various subsystems that form part of the Forrestfield-Airport Link, including being the supplier's responsible engineer for the high and low voltage traction power systems, the COM systems, and the SCADA systems on the project. I personally have a keen interest in this, having worked on Heathrow Express in the UK and now on the Melbourne Airport Rail in Victoria. Please welcome Richard Graham and Vivek Ambak.
Thank you, Julian, for that introduction. So welcome, and it's a great honor and a privilege to be able to share our experiences on the Forrestfield-Airport Link project with you. Before anything, before we go into the details of the project, it would be worth spending a few slides just to introduce who we are. Webuild is the new name of what used to be known as Salini Impregilo. We're a global leader in the construction of large, complex infrastructure projects around the world. We pride ourselves on being able to do the most difficult projects around. If it's more challenging, we're up for it. And this has been the tradition and the spirit of the company. We are now focusing on the future and trying to build a sustainable future for all of us. The world is growing, there are more people, cities are becoming more crowded, pollution is increasing, natural resources are becoming more scarce, And the only sustainable way to proceed is to create a world that is more sustainably built. On this slide, we show the four main business lines of the group. Sustainable mobility, this is basically to do with anything that reduces pollution, metros, high-speed railways, roads, bridges, and ports. We also have a long history of clean water. We have a business that deals in desalination, wastewater, recycling, incinerating plants, and irrigation and dams. Clean energy, the origins of the company were based on hydroelectric projects in the 50s and 60s. And now with everybody focused on recycled energy, this is becoming, there's a resurgence in this, particularly in the field of pump storage energy. And green buildings. Our buildings tend to be rather complicated buildings. We wouldn't typically do an ordinary office block, but hospitals, cultural centers, airports, and stadiums built with green technology. We're actually building a stadium in Doha for the next World Cup, and there's a lot of green and sustainable aspects of that project that have been incorporated in the design. A few key numbers: over 13,000 kilometers of railways, over 900 kilometers of bridges and viaducts, over 300 hydroelectric tunnels is the strength of the company, 2,400 kilometers of tunnels, over 80,000 kilometers and 83,000 megawatts of installed power. Most of that's hydroelectric. We work around the world. If we consider the entire history of the company, which is over 100 years, most of the world there on that project would be, on that screen would be red. The red that you see there are the projects that are ongoing today, with the main focus of our businesses in North America, Australia, and in Europe. In terms of money, the turnover of the company in the last year was over 6.5 billion euros. As I mentioned, the company is over 115 years old. Total workforce is in the region of 70,000, over 100 nationalities, and a very substantial backlog of 42 billion euros of work, of which 63% is related to low carbon projects. If we now focus on the project that I am project director of, Vivek and I will explain the project. We'll take you through. These are the items we will consider. We've tried to make this presentation as broad as possible, bearing in mind that the audience is probably very varied and from different aspects of the engineering world. So we'll consider the overall project. We'll consider the delivery of the project. This project is a design and construct project, so we've had all the design aspects of it, which Vivek will go into considerable detail: engineering assurance and interface management. Being a metro, this is a regulated, it's a project that comes under the regulator of railways, so there's an extra layer of assurance to be complied with. As was mentioned earlier, the core of the project is essentially two tunnels, so we will discuss them. Cross passages, which are often disregarded in such presentations. The rail systems, innovations, challenges, and learnings. And at the end, just a wrap up of Webuild in Australia. So the project is for the Perth Public Transport Authority of West Australia here in Perth. This contract was signed at the end of April in 2016, and now we're into the final throes of commissioning. So early next year, this project will be completed with real trains running, and this will have been a big milestone for not only Webuild, but also for the city of Perth. When this project was established or thought about, the economy here was in a low point, and the government wanted to stimulate the economy, and by doing so also rejuvenate the eastern part of the city of Perth, which had been a bit run down. In the process, the airport was also towards the east, so the opportunity was taken to connect the airport to the existing metro network. So the contractor is Webuild, together with our local partner NRW. The value is 1.8 billion Australian dollars, and as I mentioned, the project will have trains running early next year. Our team is a joint venture. Webuild are the leader. We have an 80% share, and NRW have the remaining 20% share. NRW is particularly strong in the resources sector here in West Australia, although they've expanded significantly since the start of this project. All these projects can only happen by people. It's people that makes these projects succeed and are delivered. We've employed over 1,500 people, over 3,000 direct and indirect subcontractors. We have 25 nationalities, and at the bottom you can see a very interesting graph showing the age distribution of the employees on the project. As you can see, with a lot of the young people, there's been a lot of opportunities here for training and apprentices, and young people have formed the backbone of this project, I think it's fair to say. Even though I've got a lot of white hair, we've relied a lot on the enthusiasm and the spirit of that the young people bring to the industry. I'll now pass it on to Vivek, who will take us through the general aspects of the project.
Thank you, Richard. Also, thank you, Julian, for the earlier introduction, and Engineers Australia for giving us this opportunity, as Richard mentioned, to talk about the Forrestfield-Airport Link project. So this project, as Richard was explaining, is a design and construct contract for the joint venture between Webuild and NRW, and a client being the Public Transport Authority here in Western Australia. So we've got design, construct, and also the maintenance of the line for 10 years post-construction. The main elements of the project involves the construction of the 2 tunnels. The project essentially is a line that spurs off Bayswater Junction, which is in the suburb of Bayswater in Perth. It's an 8-kilometer line, and it ends up at High Wycombe station, which is the last station on our line. The tunnels themselves run between the 2 portals, one at Bayswater, at about 700 to 800 meters east of Bayswater Junction, and then the other portal at Forrestfield End, where the tunnel finishes. Along the way of the tunnel, we have these 2 dive structures, as I mentioned before, and also 2 underground stations, which is Redcliffe station in the suburb of Redcliffe, and then Airport Central station, located close to the international terminal of Perth Airport. We have a 3rd station on the line, which is the High Wycombe station, and this station, unlike Redcliffe and Airport Central, is a station which is built at grade level. The tunnel is essentially divided into 3 sections, that is between the first portal and Airport Central, and then we have the second section between Airport Central and Redcliffe, and then the 3rd section between Redcliffe and Bayswater Portal. In each of these sections, we have 3 egress shafts, which are structures that, as the name suggests, is predominantly used for egress from the tunnel to at grade level, and also, if required, for access in future for maintenance aspects if you need to get into the tunnel. Along the tunnel, also what is included is the design and construction of 12 different cross passages. They're all at varying distance between each other, approximately from 300 to 450 meters separation between each cross passages and egress shaft. That largely covers off the major structures that's included within our scope on this project. We also have, as part of our scope, the design and construction of the associated rail infrastructure for this project, which includes the track work for the up and down line. We have the associated traction power and the overhead line equipments, which provide power supply to the trains. And then we have the SCADA system, which we have two separate SCADA systems on this project, one to control the traction power and one to control the buildings and station equipment, including HVAC, ventilations, low voltages, and so on. We also have, as part of our scope, the delivery of the signaling and the communication systems required for the operation of this line. And to cap it off, after construction and commissioning, we have a 10-year maintenance on some of these infrastructures, including buildings and the building services within there. So that's largely the overview of what is in our scope to deliver as part of the Airport Link project. Moving on. So the next few slides, I'll just run you through some of the three stations and give you an appreciation of where the construction is at. As Richard said, construction is substantially finished now, and we are into largely commissioning of the project. But as you can see here, this is our first station on the line, or the last station from Bayswater. So this is the High Wycombe station. It was formerly called the Forrestfield station, which was renamed shortly after award, following consultation with the community there. In here, you can see this is the at-grade station. Slightly to the south of this station is another building, which is the stowage yard, which is essentially the end of the Forrestfield line, where the train cars are stored and maintained. We also have in this location a car park. This is a multi-story car park that has a capacity of holding 1,200 cars. This has been built as part of this project as well, and to the right of the multi-story car park, you can see is our traction power substation and the high voltage substations, which provide power to the railway lines and also the services within the whole of the tunnels. In here is the dive structure, which is the entry point into the tunnel, and on top of it is the Forrestfield portal, which also houses equipment rooms carrying various rail systems in it. Moving on. So these are some more photos in and around Forrestfield Station. This is just the first one. On top is the multi-story car park, and what you can see there is a cutter head that was used as part of the TBM. So this upon direction by our client has been installed as a souvenir from the project, which will remain here in front of the multi-story car park with some feature lighting to go around it. The next photo here is a view of the platform level at Forrestfield Station. This is largely completed now, and you can see there on the retaining wall next to the platform and the track is some of the artworks which have been a feature of almost all of our stations and buildings, where we've had extensive consultation with the community and artists to come up with features that demonstrate Western Australia's various geographical areas and cultures and history. The third photo here shows at Forrestfield we also have provided the facilities for bus interchanges. So these are the busways where people essentially after embarking from trains can get onto the buses. So these are the bus bays in front of the station. The last photo here is the photo of the dive. You can see the station in the far view. So this is essentially showing the track and the signaling infrastructures and the overhead structures that we've also delivered as part of this project. The next station on our line is Airport Central Station. This station is about 200 meters away from the international terminal, which is to the right of the screen. And as you can see, the international terminal in Perth is connected to the Airport Central Station via Skybridge. This Skybridge itself wasn't part of our scope, but we had to have extensive coordination and consultations with both PAPL and the subcontractor building this piece of infrastructure that connects the airport to our station that was within our scope. You can also see here the two structures on either side of the station, the structures for the ventilation stacks, which is used as part of the tunnel ventilation system. In here are a few more photos of the Airport Central Station. The first one is a front view. You can see there the control tower for the Perth Airport right behind the station. The second picture here shows the underground platforms. The platforms themselves are about 150 meters long and is suitable to take in a 6 rail car set, which is planned for this line upon operations. The other two photos also shows the artworks that we have implemented here in ACS, similar to Forrestfield Station. This here is the station has 3 levels. One is the elevated airport level, which links to the Skybridge, and then we lead on to the concourse level. And from the concourse level where the ticketing and the passenger information systems exist, the passengers travel through to the platform level, which is below the concourse level. This escalator that we can see on the elevated airport link is supposedly the longest elevator in the southern hemisphere, which is a single span. It's about 35 meters long and 15 meters high. So that's Airport Central Station. The third station is Redcliffe Station. Again, this is located in the suburb of Redcliffe and closely to the domestic terminal. They're again similar to Forrestfield Station. It's got a bus interchange here and also a car park and outdoor car park area for the users of the trains. The Redcliffe Station, similar to ACS, have ventilation stacks and a pod that is located on the external precinct, which houses the condensers for the HVAC units and transformers and all other equipment that's required for the operation of the railway. Here we can again see a few more photos of Redcliffe Station. The station entry is at ground level. The station again has 3 levels, which is the ground level, a mezzanine level where all the equipment rooms are located, and then finally the platforms. So similar to ACS and Forrestfield, the platforms are all 150 meter long on this project. This here is a view of the tunnel. So there's a lot going on here within the tunnel. Obviously, one of the most challenging aspects of this project is the construction of the tunnel and also the fit out of the tunnel, which required extensive planning, coordination, and collaborative working with multiple subcontractors who are delivering various infrastructures located within the tunneling. Within the tunnel, sorry. So in this tunnel, just to briefly run you through the various systems that we've got. So you can see right on the top there is the overhead conductor rail, which provides the 25 kV power to the trains. This within the tunnel is a rigid conductor system. Slightly about to it, probably not clear in this picture, we also have a linear heat detector which runs through the length of the tunnel, providing monitoring of the temperature within the tunnel, which will activate any tunnel ventilation systems as required if there was to be a fire event within the tunnel. As we go anti-clockwise, you can see on top there are a couple of radiating cables. These cables essentially provide act as an antenna to provide communication services or radio services for both the carrier mobile, which is the facility to use mobile phones within the tunnels, and also for PTA's operational reasons, they use their own radio network. So these cables here provide or act as an antenna to provide coverage within the tunnel for those services. We also have, as you can see, cable containments and various services that run through it, which includes services such as the long line public address systems, fire systems, low voltage cabling for lighting and power, as we have various infrastructures of the 12 cross passages through along the tunnel, which also houses equipments which require all these connections to the major hub centers in each of the stations and egress shaft. Moving down, we have the walkway and the handrails. So that's again the walkway is right through the whole tunnel for 7.5 kilometers on either on both tunnels. Below the walkway, we have a few more pipes for fire, fire and water, and also the 22 kV HV cable that is providing power supply to each of the stations and ancillary buildings is reticulated through the tunnel from Forrestfield. So we have dual redundant supplies. So all of these are replicated in the other tunnel as well. At the bottom there, you can see is a track on top of the track slab. So that's in the tunnel, and as you can see out there in the dive is again further infrastructures. We've got some turnouts, overhead conductor rails, and at grade the overhead conductor, the rigid conductor, sort of transitions to the overhead lines, which is the catenary wire based. So that's a brief overview of the extent of the various stations and the infrastructures that we're trying to deliver as part of this project. It's a nice photo of our team at Airport Central during a visit from our Italian consulate. So in the next few slides, I would just like to quickly touch upon the various other departments that is part of such large infrastructure projects. So it's not just engineering and construction and design. There's a lot of other departments and people working for the delivery of the project, which is equally, if not as important as the engineering and construction aspects of the project. So initially is the workplace health and safety department. So they have a very critical function of ensuring the safety of all personnels working on these projects and implementing processes and methodologies and systems that needs to be followed to ensure the safety of people working on this project. So we on this particular project have a large number of initiatives that's been implemented, such as the daily pre-start briefs and toolbox talks that happens every morning in each of the sites, where people go through the work that they plan to do that day and the risk and mitigations associated with each of those works. There is extensive involvement from the leadership team, and leadership walkthroughs are conducted on a regular basis to engage with the workers on site and develop safety measures and improve on our safety performance continuously as we go through the project. As I mentioned, the critical risk discussed. We have extensive workshopping of high critical works as they come. They're discussed in collaboration with the client and the subcontractors and everyone else to make sure people are all comfortable before implementation of the works. The safety requirements have changed as we move through various phases of the project. So originally during heavy construction of the tunneling and construction of the structures as egress shafts and portals, the focus was more on that type of activities, which is now gradually changed when we get into commissioning, into the importance of electrical isolations and energy sources, and those aspects of safety are prioritized and looked at in more detail as we move through different phases of the project. To the right here, you can see some of our values that we try, basic values that we that everyone's expected to be adhering to and following to ensure the safety of the project and people working on this project. Moving on. The other department is obviously the quality department. So they have the overall responsibility of ensuring that the product that we're delivering as part of this project meets the high standards that's been set as requirements on this project. So they're continuously auditing and inspecting the various work fronts that's ongoing on the project and ensuring compliance and also identifying any non-conformances and ensuring the relevant people are actioned to to close out any non-compliances identified. So in here you can see a couple of photos of our tunnel segment manufacturing facility, which Richard will obviously talk through in more detail as we go through the slides. But the tunnel segment linings were essentially manufactured here locally in WA in a purpose-built factory, and it also had been awarded an excellence in technology and innovation for being able to perform above the industry best practices and standards for the design and manufacture of these tunnel segment lines. We also have with us an environmental management team who've got a very critical role on this project, because we work close to several critical flora and fauna areas around where the construction happens. So they implement weekly site inspections and regular system audits to ensure that all flora and fauna are properly protected, and ensuring that there are regular inspections on noise and dust and monitoring going on, so that all those aspects are covered as well. Moving on, we have this graph here shows the number of stakeholders that we are to engage with on this project. There's over 50 stakeholders on this project. Out of the 50, about 30 of them are major stakeholders who have from whom we need to have approvals for implementation of our works, and also are heavily involved with the review and of the designs and proposals that we put forward. So these stakeholders include the local government areas where the stations and buildings are located. So that's at High Wycombe, at the airport land, and then Redcliffe. We also have the airport estate itself, where there was extensive stakeholder involvement required, because the tunneling for the project was essentially running underneath operating runways at the airport. So there was extensive monitoring and stakeholder engagement as we did that part of the work. Richard will again talk through in more detail of the instrumentations and monitoring systems that we have implemented for this. There are other stakeholders, important stakeholders, such as ARC infrastructures and utilities, where relocations of major gas pipelines and works near gas pipelines were undertaken as part of this project. So again, in terms of stakeholder involvement, we've tried to be constantly engaged with the various stakeholders during design development and also during construction, to make sure there's a collaborative way of delivering this project. Going on. All right, so the next section, I will talk about engineering assurance and interface management. So this is a very critical part of the project. As Richard was mentioning before, we fall under the Rail Safety Act in terms of delivering the project and handing over. So there is a very high level of engineering assurance required, all the way from design through to commissioning and handover. And I'll try and explain some of the processes and strategies that we have implemented on this project in the next few slides. So in this slide here, you can see our design and engineering team. So the integrated design team consists of a number of players. GHD were the lead design consultants, whose responsibilities included the design of the 3 stations and the ancillary buildings, and also the associated rail systems and infrastructure. Weston Williamsons and Partners were involved with the architectural design and assisted GHD in the development of the architectural design. Geodata was involved with the tunneling design and the dive structures. Coffee with the geotechnical, and then we had Daplonia, who called Rena now, were a system engineering specialist who helped us in implementing the various system engineering processes required for the project, and also with the audit and review of what was being implemented as the project went through. We also had some partners for the delivery of the rail systems. So in here, we had awarded a design and construct subcontract to Hitachi, whose scope essentially involved the whole of the communication and the signaling system required for this airport line. And then we had Siemens, who did the traction power, and Leonardo, who are currently commissioning the tunnel and station SCADA system. So all of these, so Leonardo and Siemens, we sort of developed 85% of detailed design with GHD, and then upon selection of the actual equipment that we wanted to implement, we went out for a D&C contract to finalize the design and deliver those systems to Leonardo and Siemens. WSP here was our independent design verifier on the job. So their role obviously was to review all of the design packages and ensure compliance to the scopes, technical requirements that we had from our client. So the design and engineering team, apart from what I mentioned in the last slide, the JV, so our JV had our own dedicated design and technical team, whose major role was to be an interface between the construction works and also the design consultant to ensure that we were constantly communicating the priorities of the various design packages based on construction progress, and also ensuring the constructability and practicality of some of the design aspects. So this team has been involved with the project from day one, and it's a team that has gone through the various phases from design, procurement, and now on to delivery, construction, and commissioning to provide the design support required. So this team was also involved with the actual design of the temporary works. So we designed most of the temporary works in-house here and used external consultants when required for verification purposes. Overall on this project, we've developed approximately 15,000 issued for construction drawings that is going through now, getting as built and as constructed, and probably 20,000 and more short drawings and fabrication drawings that was developed post IFC as well. At the peak, we had around 200 people that were involved in various engineering aspects, and we had a very detailed process to ensure the interfaces between the various systems were implemented and achieved. So with regards to engineering assurance, obviously we had the technical interface management process that we implemented for technical interfaces required between the various design subsystems. And then we had a requirements management process and also a configuration management process that was all implemented as part of the overall assurance on this project. So in here, as you can read, is the RAM's target, or the reliability, availability, and the maintainability targets that we were set for on this project. So as you can see, the requirements or the reliability of the design and delivery of the rail systems essentially is very high on the project. So we had to achieve a reliability of 99.50% for the first 12 months, and then the design and the implementation needed to ensure the reliability was 99.75 for the subsequent years beyond that first 12 months. So on this slide here is a very high level of the engineering process that we follow when developing any individual subsystem. So obviously they start with the concept stage, which is which was provided to us by the client in terms of the as part of the tender process. So that brief was taken, and we developed system definitions for each individual systems and undertook risk analysis on each of these particular subsystems to end up with or as an input for the stage where all the requirements on these projects were identified. So the requirements, as I said, as part of the requirements management plan, every single requirement on this project has been identified and incorporated into the DOS database system, and every individual requirement is followed through all the way from design through to procurement, construction, and then finally commissioning and handover. Each of these requirements have to be closed out with evidences provided by each of the owners of the subsystem at the various stages of the project, so be it design, construction, or commissioning, and that is all managed and used as an input to prepare the overall test readiness and the operational safety readiness safety case that is required to be submitted to the independent safety regulator for review and approval. So on this particular project, from the contract documents, we had identified an overall 30,000 requirements. And subsequently beyond that, as the design developed and further modeling and fire engineering reports were done, there were further requirements identified. So essentially, the team tracks close to 35,000 requirements that has to be evidenced with compliance, and evidences of compliance needs to be shown for each one of these requirements. Once the requirements are identified, we went on to the stage of preparing the design and apportioning the requirements. So as part of this apportionment of the requirements, we also did a safety integrity level apportionment of various railway systems, which identified a few safety functions which had to be SIL 2 for this project, namely the most important one being the fire detection at the underground platform levels, the stair pressurization system, and also the tunnel ventilation system. All of these were used as an input while developing the design, and also during the design stages, we went through a number of workshops and risk workshops and design workshops with the client. So this involved during this stage going through hazards, HAZOP workshops, and FEMICA workshops, where all identifiable risks were identified and mitigations implemented to reduce the risk level to as low as reasonably practicable, or to assign the relevant owners to who the risk was being transferred to in some cases where design couldn't resolve hazards identified. The design goes through concept, detail, and final design stages, and each of these design stages go through a review process in itself, which is initially it goes to the JV and an interdisciplinary review process where all the other subsystems that have interdependencies with the design that under review will be completed. And following this, along with the JV reviews on constructability, the package is sent through the independent verifier who, as I mentioned earlier, WSP verifies the compliance to the contract documents. And once this is completed, it goes through a client review cycle where a client reviews it for their comments, and it's returned. So this goes through a cyclic process of concept, detail, and final before it becomes an issue for construction stage. Following this, obviously, we go through the manufacturing and procurement of the materials, and then the installation itself based on the specifications and the drawings that's been developed and approved. And once the installation construction is completed, we go through a verification and a validation stage, as I mentioned, where all of the requirements need to be evidenced as closed out with appropriate evidences before we can go on through the site acceptance and putting the railways into operation. So this is essentially a V cycle, and the engineering activities, process, and methods we've implemented is in accordance to the IEC 15288 standard that we followed. Going through the next two slides is stuff that I touched upon in my previous slide. So risk management. Risk is in everything that we do, and all kinds of risk, engineering risk, commercial risk, quality risk, subcontractor risk. Everything is identified and mitigations implemented by virtue of having workshops with various stakeholders and the client, most importantly. So we go through, as part of our project, a safety and design workshop and hazards and HAZOPs at every individual stage of the design. And that is to mainly identify the hazards, which are then transferred onto a hazard register and is tried to be closed out at the various stages of the project. Again, in here you can see these are various mechanisms or strategies we've used for engineering assurance on this project. So hazard registers, as I mentioned before, risk studies, all of these are inputs into design safety cases originally, and then subsequently into the operational safety case and the test readiness case. All of the documentations we prepare also goes through a iterative review process with the independent safety authority, and that is on top of the client review that I mentioned a little while ago. We also, as I mentioned, the JV team and the construction team are involved with constructability reviews of design packages, the maintenance reviews with the client, and then the independent verifiers and the interdisciplinary checks I mentioned before. We've also, as you can see to the left, used the BIM model for the delivery of the design, and this has been an invaluable tool for us for coordination of the various subsystems and planning of the works and delivery of the works. During the design stage, the BIM model is developed to an LOD 300, where certain level of details are included, and this is subsequently increased to LOD 400 and 500 at handover, when each of the equipments are transferred on to the asset management software that the client has, which will assist in ongoing maintenance as we go through. That leads us on to tunneling, which Richard will explain as we go through. Thank you.
Thank you, Vivek. So, as I mentioned earlier, the tunnels of this project are the key, but as Vivek has very clearly shown, there's a lot more to this project than just the tunneling. So the tunnels are 7.7 meters, just over 7 meter diameters, and the internal lining is 6.2 meters. They're twin tunnels, and in the long line below the tunnels, you can see the locations of the stations, and the little blue circles are the locations of the cross passages that connect the two tunnels one to the other. So the start of the project, of course, is the naming of the TBMs. So the two TBMs in our case are called Grace and Sandy. Grace is named after the little girl in the front of the picture. The names were chosen by children in the local school. Little Grace was quite a character and has been a great part of this project. Unfortunately, she has got serious medical conditions. She spent half her life in the hospital and half her life at home and with her children at school, always full of enthusiasm. Whenever there was a big excuse for an occasion, we used to invite Grace, and Grace used to attend. The second picture, of course, is the breakthrough, which for tunneling people is the most important event in their lives. Here we can see a cross-section of the tunnel TBM machine up at the top. Obviously, we don't have time to go into this, and I'm sure that not everybody is an expert on TBMs, but in this particular case, our TBMs were variable density types. These were virtually prototype. I think our machine was the 5th in the whole world that had been used. The principle of this machine is that the soil that you're excavating is removed from the tunnel with a slurry. And you use the slurry to create a surface or cake of the excavation face to prevent the excavation face collapsing into the TBM. So if you look on the drawing, well, first of all, if you look at the lower right-hand side, you will see soil grains, and then you see those little black flecks. That's supposed to be slurry. The idea is that you cover the face of the excavation with a layer of slurry to form like, shall we say, a chocolate paste. You then seal all the voids in the soil, and you use compressed air to press against the slurry to maintain the pressure. In other words, to resist the groundwater pressure, which is pushing the soil into the TBM. So if you look on the lower right, you will see the cutter head that's actually cutting the rock on the soil. You'll see the brown disc, which is the slurry. you will see the blue half cell, which is compressed air. Compressed air is used to squeeze down onto the slurry, and the slurry goes up that green pipe and into the cutter head to resist the pressure of the earth. In Perth and on this project, most of the tunnel was excavated underwater. The water table is extremely high, so the entire project has been constructed underwater. And the pressures, therefore, have to be very carefully controlled by this machine. The variable density aspect is if that you have a sudden drop of pressure, you can put in a very thick form of slurry to help resist the forces of the soil which want to fall into the cutter head. The composition of the slurry is a very delicate matter. It's very key to the success of the project, to the tunneling of the project, and I will address this later. The next slide is a picture that shows all the support structures that is required to support the operation of the TBM. So number one, as you can see down the lower left-hand side of the photo, is the installation for the slurry preparation. The clean slurry goes into the tunnel, and let's say dirty slurry or carrying the soil comes out of the tunnel in a closed system. We then try to recycle as much of the slurry as possible. We separate the soil from the slurry, and we send the clean new slurry back into the tunnel. It's a closed system, and we try to maintain this as efficiently as possible to make the entire process as environmentally as sustainable as possible, reduce waste, and recycle as much as we can. The second key point is the water treatment plant, point 2. Point 3 is the grouting plant. Between the segments that you install and the soil, we fill the area with grout, the annulus with grout. Number 4 is a compressed air plant. I just mentioned earlier, the presence of compressed air is fundamental. We must have compressed air throughout the entire operation of the tunnel, of TBMs. And number 5, as you can imagine, a very big power requirement is required to power the entire TBMs, but also this support structure. So this is an essential component. All this installation is fundamental to the operation of a slurry TBM. And as you can see, it's taken up a lot of space. This was located at the High Wycombe end of the project. Here we can see a cross-section of the geology of the entire tunnel. So on the right side is High Wycombe, on the left side is the Bayswater end. In the middle we have the section under the runways, the airport, and on the left third you can see the blue of the Swan River. So we tunneled also under the Swan River. The red line, the curvy line, shows the actual alignment of the tunnel, and the different colors show the different geology strata that we went through. So this tunnel has been very complicated from the geological point of view. On the right side, on the right end of the project, we had lots of sands and silts and cobbles, and towards the far left we had weeks mudstone type rock and everything in between. So the idea was to try and keep the tunnel as deep as possible. The deeper you are, the less chance you have of creating sinkholes or impacting anything on the surface. And obviously, when you tunnel through the different geological conditions, the settings on the machine have to be changed, the slurry has to be changed, everything has to be very closely monitored on this project with this type of machine. I'll just focus on a couple of challenges that we had in the tunneling. We had many, I can assure you of that, but one of the important ones was the clogging of the cutter head by what appears to be, let's say, a clay type material. So when the slurry was in contact with the natural ground, it created this thick, very, very thick, heavy, dense paste that you can see in the top right-hand photograph. This, of course, prevents the machine working, or prevented the machine working really is as it should do. It blocked the pipes, the slurry pipes had clogging in it, and very importantly is the lower picture. So the lower picture is the sizer box of the TBM. You can see what looks like two cylinders, steel cylinders. These actually rotate one clockwise and one counterclockwise, and the idea is that stones and cobbles that are excavated are crushed between these two drums, these two cylinders. So the stones fall in between, and as the cylinders rotate, you can see there are recesses. They crush the rock. In this case, the clay couldn't even go in between the two cylinders, so we couldn't make any progress until we managed to change these cylinders, for example, and try to increase the liquidity in terms of the slurry mix to remove the clay from the soil. I think at least for those of you who are interested in the tunneling, there are probably 4 key lessons which I feel would be worthwhile sharing with the wider tunneling community, if not engineers in general. The first is probably stating the obvious. Everything's done on the basis of theory, but what you actually find is not always true, as we know in life. So you only really find out, in this case, how the TBM and the system's going to operate once you actually start. It is stating the obvious, but it is a key factor. The second point is slurry, and I repeat that the quality of the slurry and the condition of the slurry is fundamental for any of these slurry type TBMs. The process plant, in other words, the picture that I showed you with all the slurry plant and all the installations, that is effectively like let's say an oil refinery. It's a process plant, and it should be designed as such. Everything is interconnected with one another. Every aspect of that is interconnected. And very typically, when you design these plants, you tend to look at the water treatment plant a little bit in isolation from the wastewater treatment plant and the power supply plant. And I think, if we have to be honest, we could have improved a little bit if we'd designed the entire system as one big system, as you would design a chemical processing plant. You'd have process engineers to design the entire system to optimize its operation. And the last point probably brings us back to the first point. You must have some redundancy and flexibility in your design. So if you really do find that you need a bigger tank for the slurry, there's space to install a bigger tank, or there is a modification you can do to enable you to increase that volume. So nothing is hard and cast. You must build flexibility into the system so that the system in entirety can be adjusted as required. As Vivek mentioned, we had our own segment plant. We had over 9,000 rings, which means over 55,000 concrete segments for the tunnel lining. This was done with a carousel type system and was extremely successful for the project. In fact, we won some awards from the Concrete Society for this very successful plant. I think we're all very proud of how this worked. The project, apart from having clogging, had many issues, as I mentioned, one of which was a leak between a cross passage. So in the middle, you can see the 2 tunnels and the outline of the cross passage. These cross passages are necessary for emergency evacuation, and as Vivek mentioned earlier, they also contain quite a lot of equipment, particularly communications and signaling equipment, once they have been constructed. Anyway, on the right side, between the contact between the cross passage and the lower side of the tunnel, it developed a small leak, and water started flowing into the cross passage. As a consequence, some of the fine sand surrounding the tunnel started flowing into the tunnel, and there was a very serious possibility that the already constructed line tunnel could collapse. There were cracks in the segments, and there were displacements, there were joints, segment joints were opened, and so forth and so on. Anyway, we managed to save the tunnel, and during that process, we installed the ribs that you see in the lower picture. We had a lot of instrumentation monitoring movements. We eventually stopped the water flow and the sand coming into the tunnel. And we then had the issue and the dilemma of we didn't have a perfectly round tunnel anymore. We were outside the tolerance to allow the trains to go through with all the OCR installed, all the tunnel equipment installed. So we had to reconstruct this portion of tunnel, which was about 150 meters. The solution that was chosen at the end was to use steel segments, graphite SGI steel segments, which you can see on the right, the green segments. These were all bolted together, and we had to chip away at some of the segments and then install and replace the inner lining with this. As you can see, the result has been excellent, and today the green is not green anymore. It's been sprayed with a fireproofing Fenderlite layer. The track is installed, and the entire all the services in the tunnel are installed. And when you go on your journey, you will not even see the difference. The next slide will shows us cross passages that I mentioned earlier. So this is the alignment of the tunnel. These are all the cross passages, 12 of them. Since the tunnel goes under the runways of the airport, there was no way we could get access from the surface to drill down and construct the cross passages. So the red dots, the 3 CP789, were excavated by ground freezing, which I will come to. The blue dots are cross passages which were created in a block of jet grouted material, which I will deal with. And the green ones were done with four-poling. In other words, they were probably the simplest, or we were in a weak rock and we didn't have to deal with lots of water and loose sand. So as you can see, 3 different types of technology used to construct the 12 cross passages. Here you can see the blue circles on the upper photos show the ring of ice that was created around the cross passage, which is the central bit. And the 2 on the bottom are 2 variations of jet grouting. So in some circumstances, because of the geology and the layers of the ground, as you can imagine, we had a complete ring if it was uniform geology, which is the 2 on the left, or you had a partial ring, whether it be ice or jet grouted, for the ones on the right. So the ones on the right, the lower part of the tunnel was actually in quite a weak rock, while the upper part of the tunnel was in a less composite, cohesive ground and was more risky to collapse. So a layer of cobbles, for example. If we move to the next picture, you will see very briefly jet grouting. So jet grouting, at the end of the day, forms a series of columns, which you can see on the right side, the right part of the picture. So you have a drill that drills a hole on the bottom, and at the end of the drill, you have a drilling rod, which has some holes in it. You pump very high pressure air, water, and grout, and as the drill is spinning round, you are replacing effectively or consolidating the space between the cobbles and the sand and filling it with this mixture of grout. So you're creating a weak concrete, which you can see on the right. The weak concrete is the grout column. As you pull the shaft of the drill up, you add on another, say, another slice or another disc of grout to the column. All the columns are then joined together, as you can see on the right. So you've created a mass of uniform, weak concrete, which you can then excavate in for building the cross passage in our circumstance. If you look on the next photograph, you will see the ground freezing solution. So we have the two tunnels on the bottom right. We have all those blue lines. These are all holes that are drilled from the inside of the tunnels. So in other words, we don't need to access this from the surface. And in these, in each hole is what you can see on the upper photograph, the vertical part. So this is essentially like a fridge. You are extracting the heat from the earth, and as you pump brine through this system, over many days, slowly the temperature of the earth becomes cold. So here we lowered the temperature to about -22, -23. So we form that ring of ice that I showed you earlier. And on the left side, you can actually see ice on the various pipes. Those white blobs are actually ice. And around the opening of the cross passage are those blue long holes that were being drilled right at the beginning. So the plant, which is the part on the top with the heat exchangers and the cooling water and the ammonia cycle, this is located on the surface, in our case, far away. So about 3 kilometers away from where we actually excavated the cross passage. So this was a very challenging aspect of the project, which I'm very glad to say went very well. So if we move on to the next picture very quickly, on the top left, you can see the start of breaking into the cross passage. On the top right, you will see the reinforcing steel and the yellow waterproofing membrane. And on the bottom, you can see a completed cross passage fitted out with the cabinets on the side, the different doors for the different equipment rooms, and the passageway for people to evacuate from one tunnel to the other in the event of emergency. Another issue that challenged us on the project is on the next slide, and this covers very briefly the instrumentation and monitoring. In this particular geology, as I mentioned, tunneling was extremely challenging, and we also tunneled under very sensitive buildings and structures, including quite close to the foot of the control tower that you saw in the earlier picture, and the airport. So usually, where possible, when you tunnel under airports, you try to divert the planes from one runway to another runway. In this case, we didn't have that luxury, so we had to maintain that all the flights kept taking off and landing as per schedule without any interruption whatsoever. Tunneling requires a lot of monitoring. In this case, we had over 8,000 instruments across the entire project, different types of instruments. So if you look very briefly at the picture on the left, you have airside monitoring, ground settlement monitoring, tunneling monitoring, excavation monitoring, groundwater, railway monitoring, structural monitoring, and everything all giving you readings in real time to a central database, a MIMS system, for managing all the information that you got. And this is accessible over the internet wherever you are. So we had constant monitoring of what is required on the project. If we move to the next slide, I will now hand over to Vivek, please.
Thanks, Richard. So the next few slides will try and explain the various rail systems that we've implemented on this project and was part of our scope. And I'll focus particularly on 2 or 3 rail systems that are critical to the operations and safety of the railway line. So we go to the next slide. So in here is a very high-level view of the various rail systems that we have on this project. So obviously the permanent way or the tracks, And then we have the traction power and the overhead line equipment, as explained previously, provides the required power and power to the trains in the tunnel and at grade levels. And then we have the traction power SCADA, which is the supervisory control system that controls and monitors all the equipments associated with traction power. And then we have the high voltage power system, which is 22 kV on this project. It is reticulated, so we get the 22 kV incomer from the local authority, and then dual redundant 22 kV supply is reticulated through the 2 tunnels into each of the ancillary buildings and stations to provide power for all ancillary or auxiliary systems that you can see here on the right. Following HV power, we have the signaling system, which is obviously very critical to the railways. And then we have the tunnel and station SCADA system. So this is this is separate to the traction power SCADA, and this SCADA systems provides the control and monitoring for most of the auxiliary systems that's listed here to the right as well. We also have, as part of this project, a widespread communication network. As I was explaining before, we have the radio networks, the backbone fiber optic cabling, the structured cabling within each of the stations, and also the gigabit system, which is the platform on which the backbone communications for most of these services happen. And finally, we have the tunnel ventilation system, which we'll go through in more detail in the next couple of slides. Again, we have, as I mentioned, these are the key rail systems, but these are all supported by a number of auxiliary systems in terms of LV power, HVAC for critical rooms and comfort of passengers. And then we have access and security for each of the sites, fire protection and detection, and also vertical transport, along with the local PA speaker systems and the passenger information systems. So if I move on to the next slide. So this is a brief overview on the traction power and the overhead line system that we've delivered. So the traction power system here in Perth is an AC traction power system. Some of the systems in the East Coast are DC 1500 DC based system, but here in Perth they follow the 25 kV 50 Hertz AC traction power system. So in here, as you can see to the right, is our outdoor substation, which is a substation where we get the 132 kV supply from the supply authority, and this is reduced to a 25 kV single phase supply in the outdoor substation, and that there is the transformer in the green bit, which reduces the voltage from 132 kV two phase to 25 kV single phase. This is then supplied onto a traction power substation, where the 25 kV switchgear is located. All of the equipment as part of the traction power were supplied by Siemens. Most of the switchgears and the transformers and the current transformers and the voltage transformers were all manufactured in Germany, and we had the main power transformer itself coming from China. This here then, the 25 kV system is reticulated as part of a underground cable for about 300-400 meters under High Wycombe's precinct. It goes into the Forrestfield dive, which is then connected onto the overhead line system. And there are a series of motorized isolators and manual isolators that allow switching operations to happen to help with the operational requirements of the client. Also, as mentioned before, inside the tunnel, we've used a rigid overconductor system. And also, as part of this project, we've introduced what is called a fixed earthing device into PTS network. So it's not a system that is currently there in PTS network or a client's network. And the fixed earthing device has been designed and implemented essentially to provide a safe way of earthing the overhead lines when required for any emergency scenarios or maintenance work regimes. So that's traction power. Moving on, I've got a brief slide on signaling and communications. So the signaling system, as mentioned before, the design and construction of the overall signaling system is being done by Hitachi. So the signaling system is based on the micro-lock to interlock processor, and we also have, as part of a system, axle counters for train detection and automatic train protection that's been implemented. Again, as part of this project, the axle counters is not widely used within the existing network, so it's being used in a very small section, but it's not widely used. So this is a significant new infrastructure or technology that's being implemented into the client's network. Communication systems, again, we have fiber optic cabling running through the whole of the tunnel and providing the backbone communications for the various systems, and structured cabling within each stations and ancillary buildings that provide communication backbone within those locations themselves. The radio systems, as I said, we are currently deploying an analog voice mobile radio system, which will be used by PTA for operational purposes, but we are also assisting with the next upgrade that the client is planning on, which is to transition the analog radio system onto a digital radio system. So the infrastructure associated with these digital radio systems within the tunnel and the comms equipment rooms and other equipment rooms are being currently installed by us to assist with the client's future planned installation of the head-end equipments to transition from analog to the digital system. One of the main challenges with regard to the rail systems is obviously the integration of all the systems that we are implementing on the Forrestfield-Airport Link back into PTA's existing operational control system or control center. So while the works themselves, the construction and the works on site have been, because it's on a greenfield project, has been largely uninterrupted and within our control. The final integration back into the control center, where all the systems that we've implemented needs to be integrated into their system, requires a significant amount of planning and workshopping and discussion with the client, so as to make sure that there is no disruptions to existing operations while we add the FAL systems onto their current system. So we've already implemented some of our existing traction power. SCADA, for example, has been successfully integrated into the existing system, and these are planned around the nighttime when trains have stopped in small windows of 2 or 3 hours when the works are completed at the main control center. The next slide here is to give a brief overview of the fire and life safety systems that we have on this project as well. So we have a fire detection system across the 3 stations and all the buildings, and additional gas suppression systems for the critical rooms, and HVAC as well, that provides ventilation within all critical equipment rooms. As I mentioned before, the safety apportionment report had identified 2 safety functions, or actually few safety functions, but the safety functions associated with the fire detection and tunnel ventilation to be a SIL2 system. And obviously the control of these systems were also supposed to be designed and delivered to a SIL2, which is a higher safety level, which promises a higher level of reliability when required on demand. So the tunnel ventilation system that we've got consists of a number of fans at the portals and the 2 underground stations, arranged in a duty standby configuration, along with a series of dampers and ductworks that provide this functionality. The tunnel ventilation system overall is designed to provide two functions. One is obviously the smoke management in case of a fire scenario in either the tunnel or the stations, and in 99% of the time in other situations, it is also designed to provide ventilation for station comfort for passengers and everyone else. So there was a few challenges we came across with regard to the design of the tunnel ventilation system, especially at the airport central station. We identified that through the modeling that we did, the CFD modeling for the smoke scenarios, that the originally designed position of the exhaust would have caused the smoke to sort of hinder the evacuation pathways and, more importantly, the control tower, which was located next to the airport central station as well. And there had to be a redesign of the tunnel ventilation system, exhaust system, where, as I showed you in the picture of ACS earlier, resulted in 2 separate ventilation stacks located at the far ends of the station box, and also the implementations of additional wind sensors, because the ventilation system was required to operate in a different mode depending on the direction of the wind, which was identified to be changing during the course of the day. All of these tunnel ventilation modes are controlled from our SCADA system, so it is all automated completely, with also the option of allowing it to be operated in manual if the operator in the control center wishes to do so. The SCADA system as well has been designed to SIL 2 and is currently going through a rigorous amount of testing and commissioning to satisfy the requirements of a SIL 2 system. There's several other rail systems that we are delivering, as I mentioned, on this project, but it's because it's such a wide topic, I've tried and limited myself to discussing the 3 main critical systems required for the operation and safety of the rail network. Moving on to the next slide, I'll hand it over back to Richard, who will talk through the innovation challenges and learnings.
Thank you very much, Vivek. So, as you can imagine, a project of this size, and I think you've gathered already from the presentation so far, we've certainly had our fair share of challenges, but we've also had many successes, and as always, you always learn for the next project. So one of the main issues, as I mentioned, was keeping the planes flying while we were tunneling underneath, and we had to develop a system of monitoring the settlement of the runways as we were tunneling. We chose laser surveying equipment with reflectorless targets from a series of 18 robotically controlled theodolites, effectively. I won't go into the detail except to say that these were installed on the sides of the grass verge on the sides of the airport. It took us over two and a half years of negotiation, explanation, development, and to reassure not only Perth Airport themselves, but also the Civil Aviation Authority from the federal level in Canberra, that our system was extremely low risk and wouldn't affect the flying of the aircraft and injure and even risked a laser ending up in the eye of a pilot of a landing aircraft. So it was very challenging, and however, it succeeded, and we managed to mine without interrupting anybody. The track slab, we saw the picture earlier, and there's a very nice picture here on the right. Originally, the design was to have standard reinforcing steel. We removed that and replaced that with fibers, plastic fibers, and the entire track was poured with fiber reinforced concrete. This made it much easier to pump. The pumping of the concrete was up to 2.5 kilometers long. And this, I believe, is another record on the project. It was the length of pipe and pumping of concrete. This was a very significant impact. A, it speeded up the work, and B, it saved all the steel, and therefore it was a very significant sustainable win for the project. We also had installed a lot of solar panels and reduced the energy consumption on the project. The final design, especially of High Wycombe Station, all the roofs are covered with solar panels. The recycling of water, I mentioned earlier, of the big plant, of the TBM recycled water, Somebody has calculated very kindly for me that we have saved over 1,000 Olympic-sized swimming pools of water. So that's a significant amount, especially here in Perth, where virtually all the water comes from desalination plants. So water is a scarce commodity here, and therefore this is a very big, important saving. The solar panels will, over the life of the project, which is 120 years, have saved over 36,000 tons of CO2 over the life of the project. It cannot be scoffed at. Challenges that we set ourselves at the beginning, and we probably didn't fully understand until we come to the end. Certainly mining under operating runways and a big railway network actually for arc rail was challenging. The instrumentation I've just mentioned, that was a very big exercise in its own right. The different geology here for tunneling, geology is fundamental, and it all revolves around the quality of the ground. 120-year design life, this is normal for these type of projects. Interfaces, as you can imagine, many interfaces, not only within our own organization, but with all the external stakeholders that we had to deal with. And there are a number of portions of the project which are built very, very, very close to high-pressure gas pipelines. The main gas pipeline taking gas to southwest Australia was less than a meter away from our tunnel, and work that we had to do around that. So you can imagine the criticality of that. And of course, tunneling in itself is a very logistics-driven activity. And the key to the success of the project is not so much the excavation per se, but it's all the management of the logistics around it. As lessons learned, flexibility, I think I touched on that earlier. Again, stating the obvious, the better you prepare for your work, the better the outcome. We always think we've done as much as we can, but looking back with a very cold view on the situation, you can always think you can have done better. And managing the media. At the beginning of the project, we were the main project in this city. Now we're probably less interesting to the people at the beginning, to the population, but at the beginning we were very much in the public eye on this project. So at the beginning of the presentation, we reflected on Webuild around the world. You remember the map with all the red countries. And just to bring it back home to Australia, where we are, Webuild have been here since quite a long time. We actually worked on the Melbourne City Loop about 30 years ago. We then, for some reason, went away, but we are now very much back. So the yellow markers show where we are active today. So Perth is and Melbourne, where we are doing the new the Northeast Link project, which was recently awarded, and the little yellow number 2 is the Snowy 2 pump storage project, which is very close to the heart of the people of Australia. We're here to stay, and we're here to help develop the long-term infrastructure plans of the country. So thank you very much to everybody.
Thank you.
Well, thank you, Richard and Vivek. That was a fantastically complex project, clearly, and we've got some suitably technical questions for you both. So I'd like to welcome Richard and Vivek to join us back again. We'd like to run through some of the questions. If people do have questions, please do so, put them into the chat box, and we'll try to answer them if we can. If we don't get a chance to, we are running a bit short on time, we'll try to get back to you separately. So if I can bring us back, okay. Maybe first question, Vivek, to you from Kane in South Australia and from Ryan in Queensland. What sorts of technologies were used to future-proof the tunnels from changing environmental conditions and transportation requirements? And also, were there any vertical transportation innovations that were identified? So I think it's muted. think.
Yeah, sorry. So I was on mute there. So in terms of the future proofing of the tunnels, from an environmental perspective, what we've done is we've obviously installed future cathodic protections along the whole of the tunnel and the cross passages. So that is to protect with corrosion. The design life of the tunnel is 120 years. So we've made provisions along the whole of the tunnel segments and other structures for cathodic protections. In terms of technologies and within the tunnel, obviously the technologies are changing rapidly year on year. So as I mentioned in my presentation, we've made allowance for the change of the radio systems from analog, which is currently used by a client, to a digital system in the future. We also have space proofing and of the cable containments and the cross passages and the equipments within the cross passages to cater for any future requirements of the client that would come up. In terms of the second part of the questions, innovations for vertical transport, the requirements of the vertical transportation systems mainly originated from the pedestrian modeling that was completed by our consultants. So there was not much innovations or much leeway in terms of what we could provide from a vertical transport system. But within the system that was provided itself, there was a number of innovations or sustainability initiatives that were implemented. So we use variable frequency drives for energy consumptions, LED lightings on the escalators and the lift, and regenerative braking is another aspect that was used with the escalators for energy saving purposes. They were the main innovations in terms of vertical transport. Again, as I mentioned in the slide, at Airport Central, we've installed a rather long, or the longest escalator in the southern hemisphere, single span. So that was particularly challenging, and there are provisions made for future escalators and lift within each of these stations as well.
Yeah, really a lot of opportunities there to innovate, right? Maybe Richard, one for you from Hamid in Victoria, and from Jason Liu as well. What were some of the driving factors for the cross passage spacing, and at sort of 300 to 400 meters spaces? What were some of the fire life safety criteria, and how were they satisfied?
So those are very good questions, particularly here and particularly for the portion of the tunnel under the runways. Since the only possible access, or rather the area of the tunnel which wouldn't be affected by any sinkholes, was effectively those triangular pieces of grass that you invariably see on an airport between the runways and the parking areas. So essentially a cross passage had to be between a piece of grass on the surface, two pieces of grass on the surface. So actually the longest distance between two cross passages is around 500 meters, one portion of about 500 meters. The international fire standards generally talk about distances of 240 meters between cross passages. So we couldn't comply with that. In the end, we undertook a very detailed quantitative risk assessment of the entire spacing of the tunnel, of the cross passages. This was a very lengthy exercise. It was very comprehensive. It was done in a lot of detail. And we managed to show that by having variable spacing and all more than 240 meters, we were not impacting on increasing the impact on the loss of life. So issues that are taken into account are whether you have walkways, the composition of the actual trains, the materials the trains are made of, the number of passengers, the value of life, frequency of trains. All these aspects were put into this assessment, and so far analysis was undertaken, and it is shown that the installation that we have today is no more dangerous than the one with a conventional 240 meter spacing. So I would suggest in future on these projects, a detailed quantitative risk assessment be undertaken, and I think you could optimize the distances between the cross passages, which are always very difficult to build. They are a very risky portion of tunneling. The tunnel itself is maybe less risky, but when you start connecting the two tunnels and you haven't got that TBM anymore, the challenges increase many times over.
Yeah, like you say, lots of no shortage of challenges, right?
Mm.
Maybe one for both of you, and this is from Robert in Queensland, Raymond Ho, and Selwyn Rays have all raised similar questions relating to the digital side of things. You mentioned that you've done the design in BIM, and were there any considerations for how these digital assets might get integrated into the SCADA systems and then into an operational digital twin? And how did the modeling help really with being able to deal with modifications that might have cropped up, relating to design footprints or drawing conflicts that might have come up during either design or construction? Maybe Vivek, if you'd like to go first.
Yeah. So the BIM model, as I mentioned, is during the design phase done to what's called a level of detail of 300, and then eventually during handover it's done to LOD 500. So that essentially means all of the asset management details of every piece of equipment and asset that we are introducing into the PTA's network is identified and populated within the BIM model. We extract this information into PTA's existing asset management system, which is called Ellipse, and the Ellipse system is currently integrated to the SCADA system in PTA's head-end control center. And when we introduce FAL into their existing system, this will be an extension of the asset management system being integrated with the SCADA system. The intention being that if alarms or faults or indications of any sort were to come on the SCADA system, it would directly interface with this asset management system in PTA's network to produce asset orders or maintenance orders, and the relevant subcontractors are notified as part of that process to do remedial works. In terms of how it was used for design purposes and conflicts with other drawings and all of that. So the BIM model was one large model where we had each of the subsystems as a subset of models within the bigger model. So clash detection was a large piece of this whole exercise to ensure that all the different subsystem engineers, so hydraulics, cable containment, fire detection, everything that needed to be installed and space-proof were done in a manner that conflicts or clashes were avoided as much as possible. Of course, no system is perfect, so we use this BIM tool as we progress from design on to construction, because most of the shop drawings and fabrication drawings were prepared by various subcontractors and our own design and technical team here. And we continued using this BIM model to ensure clashes and clash detection was carried out prior to installation, because it results in a lot of time saved. If you don't have so many clashes you have to resolve on site. So yes, overall it was a very useful tool on this project, and also visualization of things that being built on site was possible through this medium, a lot better than through maybe a 2D drawing or a CAD file.
So
Richard,
on the
anything
changing,
else?
so on changing requirements, the big car park at the beginning of the line at the Forrestfield end was a variation to our contract. So this was an extra, shall we say, big extra. The changing in standards, as during the life of the project, there have been certain revisions to international standards, to Australian standards, and we of course have to keep track of these. Some of these have an impact on the work that's been done, particularly in the design phase. Some of them probably are more procedural rather than of substance, but certainly there are one has to be fully aware of all the changes in the industry, whether it be on the electrical side or hydraulic side or fire regulations, safety regulations, and also the safety regulations in terms of the operational approval from the regulator, the rail regulator, and the Independent Safety Authority, the ISA. So you have to be aware of everything that's going on and all the changes that are going on in the technical space throughout the project. It's a moving. Nothing is fixed. It's always moving, always changing. Some big changes, some small changes.
Vivek, maybe a quick question for you. Mark from New South Wales and Glenn Hale also raised this one. What sort of advantages did you have around having the rigid overhead power lines versus other wide overhead conductors, especially in the underground?
Yes, so on this project, as I mentioned, so we have a combination of both the catenary wire and the rigid conductors. The rigid conductors are obviously used within the tunnel environment. The tunnel environment or the clearances within the tunnel is obviously, as you can appreciate, not equivalent to what you would have at grade level. So you're forced to sort of go down the path of using the rigid conductors within the tunnel, which operates with much lower clearances compared to catenary, and also from an overall reliability and maintainability of that asset within the tunnel, a rigid conductor offers you a much better option compared to the catenary wire options that is more predominantly used outside tunnel areas at grade levels.
Look, thank you both very much for your time today, and I think we're probably out of time. We've gone over time, but that's been a fantastic presentation. I'm sure a lot of really interesting facts that people would have picked up there, and there are a number of questions that we'll try to get back to people individually afterwards. Please join me again in thanking Richard Graham and Vivek Ambak for the time and insights today, and also to Engineers Australia and the industry partner Webuild for making today's webinar possible. We'd like to appreciate your feedback from everyone today on the program to help us improve for future sessions, and also there is a short feedback form which is linked in the description box below. Thanks again for joining us, and we hope to see you at our next webinar. Thank you.